We have a deep, built-in bias when it comes to biology. Because life thrives here, we assume Earth's exact conditions are the ultimate standard for living things. We've spent decades and billions of dollars operating under that assumption, having scoured our immediate neighbors in the solar system looking for a match. We've probed the barren rock of Mars, peered beneath the crushing atmosphere of Venus, and scanned the frozen, cracked shell of Europa, hoping to find something swimming beneath miles of ice. Yet our local neighborhood appears completely empty. Measuring the rest of the universe against Earth is a flawed premise. Our planet is highly vulnerable, operating under severe biological deficits and governed by a ticking cosmic clock. Take a look at this timeline charting the 10 billion-year life cycle of a G-type main sequence star, the exact kind of yellow dwarf we orbit. We are currently nearly halfway through that entire life cycle. In about 5 billion years, our sun will expand into a red giant, completely consuming Earth and incinerating any remaining biology in the process. Earth functions as a fragile starter home. To find environments that offer objective upgrades to our planet's specific flaws, we have to look deeper into the galaxy for what astronomers call superhabitable worlds. Our first major deficit is evolutionary time. Life on Earth has been evolving for roughly 4 billion years. While that sounds ancient, it is actually a relatively short window for biology to develop when you consider the vast age of the universe. This comparative bar chart highlights the solution. On the left is the 10 billion year run of our yellow dwarf, and on the right is the lifespan of an orange dwarf star, like the one hosting the planet KOI 5715.01. These stars burn slightly cooler, making them incredibly stable, hanging around for up to 70 billion years. Think about the biological implications of that much time. If humanity evolved in just 4 billion years, 70 billion years of uninterrupted evolution provides a window for levels of biological and technological complexity we can barely conceptualize. This is where we begin to speculate about Dyson spheres and the peak of planetary civilizations. The catch with KOI 5715.01 is purely physical. It is 3,000 light-years away. If we secured a modern vessel like NASA's Orion spacecraft today and launched immediately, it would take over 100,000 years to reach the system. We have to look much closer to home, to a system just 39 light-years away, known as TRAPPIST-1. The worlds in this system are significantly older than Earth, offering life a 3 billion year head start before our planet even finished forming. We know these planets exist through a technique visualized in this diagram, known as the transit method. Astronomers spent years measuring the TRAPPIST-1 star, watching for the exact moment its brightness dipped as a planet's silhouette passed directly between the star and our telescopes. Through this method, we identified TRAPPIST-1e, an Earth-sized world sitting right in the habitable zone. But its host star is a tiny, cool red dwarf. To stay warm, TRAPPIST-1e orbits extremely close to it, a proximity that causes a gravitational effect called tidal locking. One specific side of the planet is permanently fixed facing the star, getting endlessly cooked, while the dark side freezes. Any life here would be restricted to a single thin twilight strip dividing the two extremes. But that tight orbit creates a spatial environment unlike anything we have ever experienced.
The 7 TRAPPIST planets are packed so closely together that you could stand on one and see the others dominating the daytime sky. Interplanetary travel here would require the same logistical effort as booking an international flight on Earth. These systems perfectly solve Earth's lifespan problem, granting biology billions of extra years to mutate and grow. But they exact a heavy toll, forcing life to adapt to permanent extreme twilight zones, or placing the planets entirely out of humanity's physical reach. There is another major assumption we make about our safety, centering on the massive gas giants in our outer solar system. For decades, the consensus was that Jupiter acted as a cosmic shield, using its immense gravity to attract stray asteroids and protect the inner planets. Recent orbital simulations show the exact opposite. Jupiter's immense gravitational wake can alter the trajectories of distant debris, hurling more asteroids directly into the inner solar system than if it weren't there at all.
A true upgrade in planetary safety is Kepler 452b, a world often dubbed Earth 2.0. As far as our data shows, it is the only planet orbiting its star. Without a gas giant to stir up local debris, models suggest a lone planet like this would experience 3.5 times fewer asteroid collisions. But look at this scale comparison to understand the brutal physical trade-off. Kepler 452b is classified as a super-Earth, meaning it is 50% larger than our home. That extra mass means any visiting human would be subjected to double the gravity, making you weigh twice as much the second you stepped onto it. If a species can survive that crushing force, a larger planet offers a solution to Earth's final major deficit: limited contiguous biomes.
Our oceans are relatively shallow and broken apart by shifting tectonic plates, putting a hard cap on how large and expansive marine ecosystems can grow. 600 light-years away sits Kepler 22b, which solves this fragmentation entirely. Current observations point toward this super-Earth being a true water world. There are no continents here to interrupt biology. It is a single, uninhibited global ocean that stretches hundreds of kilometers deep, offering a boundless canvas for aquatic life to thrive. Finding worlds that solve our asteroid threats or our limited landmasses is entirely possible, but those environments come with hostile conditions, where human physiology would either be pinned to the dirt by gravity or drowned in bottomless, dark waters. This creates a difficult paradox for astronomers. A planet being objectively better for the long-term evolution of biology does not mean it is better for human beings. If we were magically transported to any of these superhabitable candidates tomorrow, we would immediately perish. Our bone density and cardiovascular systems cannot handle double gravity. Our crops cannot survive on a tidally locked twilight strip, and we have no means to establish a civilization floating on an infinite ocean. The specific flaws of Earth, the ticking clock of our yellow dwarf star, the constant threat of asteroid impacts, the fragmented, shallow landmasses, are the exact, highly specific calibrations that forced human physiology to adapt and evolve into what we are today. The universe is statistically filled with planets far superior to ours for the long-term, billion-year survival of biological material. Exploring these superhabitable worlds proves that Earth is not the absolute pinnacle of cosmic real estate. It is merely one modest, temporary variation in an expanding universe of possibilities.